Okay, so for chapter 35, I'm going to do problem 14, 35, 39, and 40. So let's start with the problem 14. So if you look at the problems here, it says in a double slit arrangement, the slits are separated by a distance equal to 100 times the wavelength of light passing through the slits. And you're asked to find the angular separation in radians between the central maximum and the adjacent maximum. And the second part asks you to find the distance between the this maximum on the screen. That's 50 centimeters from the slits. Okay, so the diagram. So we can now draw the diagram like this. So we had, let's say this is where the slit is located, and this is where the screen is located. And the separation, which is given, we use a symbol capital D to indicate that the separation between the slit and the screen, which is 50 centimeters. Okay, and that draws horizontal line to indicate that the central, central maximum occur. So this is on the screen. So this will be the central maximum, and this is your first order, and the second order, and symmetrical about the central maximum. So this is m equals to 0, and this is 1 and 2 and so forth. Okay, and says that the wavelength is 100 times the slit separation. So the slit so let's say this is one slit and this is two slit, the slit separation, which we use a lowercase d. So slit separation is 100 times the wavelength. Okay, and then you want to find, based on this information, you want to find the angular separation. So this is m equal to 1. So in other words, you want to find out what is that theta 1. So this is the double slit interference pattern. And so the bright fringe, the bright fringes can be found by using this equation, d sine theta. D sine theta, that's equal to m lambda, that's for bright fringe. And m, when m equals to 0, that's a central maximum. And when m equal to 1, that's the first, that's the first order maximum. So you have the d and then sine theta 1. That's equal to m is equal to 1 and that lambda. And then because d is 100 wavelength, so you plug into here. So you have the sine theta 1. That's equal to 1 over 100. So from there you can calculate your theta 1. So theta 1 you will get 0.573 degrees, and that's equivalent to 0.01 radians. Okay, so so this is basically how you do part A, just by applying d sine theta, that's equal to m lambda, and m is equal to 1. And so from there you can calculate the angles where the first maximum is located. And once you find the degrees, of course, it's very easy to convert it to radians, because you would just multiply this number by pi and divide it by 180. Okay, so that's part A. Now for part B, it says, what is the distance? So what is the vertical distance between those two maximum? And we know that this is this just by basic trigonometry, we know that you can do tangent theta 1. That's equal to this distance, that's called a y1, and over this distance, which is capital D. Okay, so you have the angle here, so you can just plug in there, and your D here is 50 centimeters. So you can quickly calculate your Y1, and you should be able to get a numerical value that is about 0.005 meters, which is 0.05 centimeters. Okay, so that's basically how you apply the d sine theta equals to m lambda to a double slit interference pattern in order to determine the angular display locations of the maximum on the screen. Okay, so that's problem 14. Now, problem 35, let's look at problem 35. Let me just go down a little bit. Problem 35. So for 35, let me erase this. So problem 35 says that we wish to coat flat glass with a transparent material so that the reflection of light at wavelength 600 nanometers is eliminated by interference. What minimum thickness can the coating have to do this? So this is a thin film interference, and you want to coat glass with the material. So we can draw a diagram like this. So this is glass, and we wish to coat a material. So that is the material, and then this is air. Okay, so I'm going to call this N1, N2, and then N3. And the N1 has an index of refraction of 1. N2 has is 1.25, and then N3 is 1.5. So whenever you do the thin film interference, the first thing you identify is that how N1 is compared to N2 and how N2 is compared to N3. So you can see that N1 is the smallest, and it gets progressively larger, meaning that N1 is less than N2 and is less than N3. Okay, so there wouldn't be any phase change due to reflection. And so then the problem says that you want to find the thickness of the coating just so that the wavelength at 600 nanometers is eliminated. In other words, you want to use the equation that is good for darkness, because you want to eliminate that wavelength. So if you have N1 less than N2 less than N3, then the equation used to find the minimum or the darkness will be this one, the 2 times the thickness. So this is the thickness, 2 times the thickness of the material, that must be equal to M plus 1/2. And then the wavelength of light in our material, which is lambda over N2. Okay. And then the minimum thickness, as you can see, the thickness of the coating is related to M plus is proportional to M plus 1/2. So for L to be the smallest, your M has to be smallest as well. So the smallest value from this will be 0. So you will have the 2L that's equal to 0 plus 1/2. And then you have your lambda, which is 600 nanometers. I'm going to keep nanometers. And you have your N2. N2 is 1.25. So when you plug in the numbers here, and then you will be able to get your L. And your L is equal to 120 nanometers. So you can either keep it in nanometers or convert it to meters. Doesn't really matter as long as they are the same. So it's 120 nanometers or 1.2 times 10 to negative 7 meters. Okay, so this is a very basic applications of the thin film theorem. You will have the identify the n values, and then see which one, and also because you want to find light is being eliminated. So this is the equation to use. Okay, and then you just plug in the numbers, and then you'll get your L. Okay, and then the next one I want to do is problem 39. So let me. So problem 39. Let me scroll up a little bit. All right, so problem 39 says light wavelength 624 nanometers is incident perpendicularly on a salt film suspending in air. So we know that the film is sandwiched by air. what are the least and second least thickness of the film for which the reflections from the film undergo fully constructed interference. So in other words, we want to find a condition that is that has a brightness that will produce a the bright fringe. So again, I'm going to do this. So I have my air, I have my soap, and I have my air again. Okay, so I'm going to call this N1, N2, N3. This has 1, 1, and this has 1.33, the index of refraction. So you can see that your N1 is less than N2, and your N2 is greater than N3. So this will cause the phase change by reflection once. So for brightness, the equation to use is this: 2L that's equal to n plus 1/2, and then lambda over N2. Okay, and so for in this case, so part A says the least thickness. Again, what is the smallest L that would produce a constructed interference? That would be when M is the smallest. So when M is equal to 0, then we will have 2L that is equal to 1/2, and then the wavelength, which is 624. I'm going to keep it the nanometers, and N2 that's 1.33. So from there, you'll be able to deduce to calculate your L. In your L, you should have the value of 117.7 nanometers. And for part B, it says what is the second least thickness, meaning that you want to go up, M will have to go up a little bit higher. The next one will be when M is equal to 1. So you have the 2L that's equal to 1 plus 1/2, and then 624 over 1.33. So then you'll be able to get your L, and you have your L that's about 351.9 nanometers. So this is, when you have a wavelength that is 624, and when you want to produce a fully constructed interference, then this is the thickness of the soap film that has to be in order to produce the brightness, and the next thickness will be this this value just by applying this equation. Okay. All right. So the next one I want to do is again a thin films thin film interference, but this is a little bit okay. Let me just go here. This is more this one give you another way to look at this problem. So a thin film of acetone coats a thick glass while its incident normal to the film. In the reflections, fully destructed interference occurs at 600 nanometers, and fully constructed interference occurred at 700 nanometers. Calculate the thickness of the acetone film. So again, you have the 3 layers, okay, and so you have the glass, which is the last one, and acetone is in the middle. And here is the air. So you have the N1, you have N2, and you have N3. And your N1 has 1, your N2 has 1.25, your glass has 1.5. So you can see that your N1 is less than N2, is less than N3. Okay. So when you have the condition like this, then there's no phase change produced by reflection. So for bright fringe, this is the equation, which is 2L that's equal to with M over M and then lambda over L2, N2, okay? And for dark, then that'll be 2L, that's equal to M plus 1/2 L of lambda over N2. So for the bright fringe, it says that constructed interference occurs at 700 nanometers. So what we can do is that we can say 2L, that's equal to M, and then 700 nanometers over N2, which is 1.25, okay? And so from there, we can see that your L from the bright fringe is equal to 280 and then times M. So you might wonder, why didn't I put M equal to 1? Because it didn't say which order that it occurs. So we can't just say that, you know, it is equal to 1. And then for the dark fringe, the equation is 2L, that's equal to M plus 1/2, and then lambda over N2. So we can plug in the numbers. So 2L, that's equal to, again, we don't know what M is, and then plus 1/2, and then times the your lambda. When this fully destructive, which occurs at 600 nanometers, and then over 1.25. So there we get my L is equal to 240, and then M plus 1/2. Okay, so this L must be equal to that L because the same thickness. So from there, we can actually figure out what M should be, because you have 280 M, that's equal to 240, and then M plus 1/2. So from there, you'll be able to figure out your M must be equal to 3. Okay. So once you have, once you have the M equals to 3, then you plug into either one of them. Then you can calculate your L. So your L is 200 and then times 3. So that will give you 840 nanometers. Okay. So this problem is a little bit different from the previous one because we didn't know, it didn't specify, it didn't specify whether it's the smallest thickness or the what. It just, but we do know that the L here has to be the same, when the brightness occur or when the darkness occur, given the specified wavelength. So that's why you want to apply the equations, one for the bright fringe and one for the dark fringe, and then set that equal. And then once you know how L in relation to M, and then because L has to be the same, you're using the same film, so L has to be the same. Then you can set them equal to each other to calculate your M, and then once you have your M, plug into that one to give you the thickness. Okay, so that's basically how you would approach this problem.